Looking at this band reject filter, we can see that it is in the parallel form. An example of this is in the notes linked below the like button on page 124. These will include the actual equations, or not equations, but transforms that we're going to be using to calculate our omega naught, our f naught, q, and the rest of our problems. So going to find these things, we have our circuit diagram here. Now we're given the H of S form of this, so we don't need to do the voltage divider and all that stuff, but it is important to note that we would do voltage divider to actually get to this point. Now we need to calculate our omega naught, and our omega naught for band reject, and it's in parallel like this, we are going to have omega naught equal to the square roots of 1 over our L times C. And our L is going to be the 50 microhenries. Our C is going to be the 20 nanofarads. So we're going to plug these into the denominator right here, underneath 1, and then square root the whole thing. This is going to give us approximately 1,000 kilorads. Remember, it's in kilorads, so it's not going to be exactly 1,000. It's going to be approximately, let's see, 1, 2, 3, something like this. And because it's in kilorads, currently it's in rads per second, we'll multiply it by 1 kilo over 10 cubed, and this means we'll have to move the decimal over this many. And so this would give us 1,000. Now we need to calculate f naught. Well, the formula for frequency is where we have our omega equal to 2 pi f. So we're going to have omega divided by 2 pi, and this will be equal to our f. You just throw a naught underneath both of these, and we have that our frequency is 159 kilohertz. Now we need to find q, and our q can be found two different ways. Our q can be found when we have our omega naught over the beta. We haven't found our beta yet, so instead we're going to do the square root of our r squared c divided by L. Now our r is going to be the 750. We need to square it, multiply it by 20 times 10 to the negative 9 for this nano, and divide it by 50 times 10 to the negative 6 for micro, all underneath this square root here. And then this is going to give us 15 for our q. Now we have the omega c1 and omega c2. I've included the formulas right here that we would use to actually find them. It's a lot to plug in, but after we plug these in for the omega c1, we are going to get 967 kilorads per second. And then for omega c2, we plug it in here, and then we would get exactly, well, approximately 1034 kilorads per second. Now we need to find our beta b. And to find beta, there are, just like in looking for q, two different ways we can do this. Our beta is equal to the omega c2 minus omega c1, and this is equal to 1 over rc. Now, I prefer to do it like this, that way we can see what we're actually solving for. We're solving it for the omega. Now, when we look at the problem, we can see it's in kilohertz, not in rads per second. If it's in rads per second, then we're solving for radians, or we're solving for our omega, sorry. But since it's in kilohertz, we need to convert this to frequency, and we're going to use this equation to convert from omega to frequency. But we can first find our omega. So b in the omega form is going to be 1034 minus 967. And we've gotten these from our omega c2 and our omega c1. We can see that we're subtracting them here, and then we've found them right there. And so subtracting this, we are going to get that our b is equal to 67. So we're going to take this 67, and then we are going to divide it by 2 divided by pi, and that's from this right here, because we want to calculate frequency. Currently, again, it's in rads per second, and we want to have f equal to 67 divided by 2 pi. So this is going to give us approximately 10.7 kilohertz, and that's how you would go about looking at this parallel band reject filter.